Okay, so check out this video. Company out of Boston called Boston Dynamics. That takes some of that glare off of that. Okay, so check this video out. We won't spend too much time, hopefully, talking about it. I don't know if we're going to get audio or not. See what happens if I do that. Let everyone watch it. Let me tell you the ending. Now that's awesome. They are. But they're going to wait for us to mount weapons on them first, though. I mean, the algorithm required for that is just, I mean, just imagine what it requires to balance. I mean, we take for granted what our brains can do, right? But, I mean, that's incredible. I was most impressed when he kicked it, when he was just standing there and it recovered from that. I mean, that's incredible. I'd love to be that guy working for that company right there. I mean, that they're breaking ground right here. This is big time stuff. Of course, watch this. Watch the way they turn, and I think one of them goes down faster than the other. I mean, it's just constantly adjusting and correcting, and right. And this is their new, I think, their new robot. They're going to show here in a second their older prototype, which was this big beast. Yeah. But that big one, that's the end of it. Show you one more. That big one looks all clumsy, right? But check this out. It's gas powered. Come to life. I don't. No. Watch this once it gets into a full run. Yeah. All right. Anyway, I found that video to be pretty inspiring. Maybe not quite as inspiring as this, but inspiring nonetheless. All right, we're going to pick up where we left off. Actually, everyone click in. All right. So what I'd like to do is, I know that there are probably questions over homework. I would like to try and work through today's material. I think I might address some of those questions within today's lecture. If not, get with me after class, or if we have time at the end, we can discuss it. We are going to cover partial fractions today, and I just made up these notes for this section, finished them up yesterday, and posted them on the web, so I didn't expect people to have them, so I just brought copies. So take some of these, pass those around. If there's any extras, just leave them on the tables, and I'll get to those later. The quizzes that you did at the end of class last time, I do not have them ready. I gave a calculus test yesterday, and I graded that instead of grading your quiz. All right, partial fractions is the last technique of integration. And it really brings together everything we've done up to this point. All right, one partial fraction problem can incorporate almost everything we've seen in one problem. So I apologize about the font on the printout being so small, but I couldn't get it to, I was trying to get it to all fit on just a few pages. So let's get started. First thing, I'm going to point out some preliminary things for this section. We all need to be fully aware of Formula 17, which was our arctan formula. Now, the arctan formula that we used, that we've been using, I should say, has always been like 1 over x squared plus 1. But if we replace x with u and we replace the 1 with a squared, then the formula changes a little bit. You have to compensate for that a by putting a 1 over a in front of the arctan. And then within the argument of the arctan, you must divide your variable by a. So please just be aware of that formula. It'll be used throughout today. Now, on top of that, we have some other integrals. Now, it's going to look a little different than the way it looks on your notes. Some other integrals that right now we should be able to handle, and we should be able to do them fairly fast, all right? So what I want to do is go through each of these 8 integrals as fast as I can, just so when we see them later, we realize, hey, we can handle that, all right? So the first one, this is what I didn't write on your paper, is when we have a constant divided by a linear expression. So anytime we have a constant divided by a linear expression, we can pull the constant out, and that looks very much like a 1 over u, doesn't it? And the antiderivative of 1 over u is natural log. Now, we also have to make sure that we take into account the a in front of our linear expression, right? The a in front of the x, in this case it's 1, so I don't really have to do that 1 over a part because it's a 1 in front. So what should this become? 2 natural log x minus 4 plus c, and we're done. So from here on out, if we ever get a number divided by a linear expression, we should be thinking we've got it, all right? That's A. Part B, or that's 1, sorry, this is 1. The second problem is the same thing, linear, constant over linear. What's the only difference between this linear and the one before? We actually do have an A, right, other than 1, but this is a linear expression. Constant divided by a linear expression. So I already know the antiderivative of this is going to be 1 divided by A. A here for us is what? Negative 5, right? So I need to come in, I need to put in a 1 over negative 5. You could just write negative 1/5. Then, natural log 4 minus 5x plus c. This 1 over a thing, I talked about this in a previous class. If you have a function and you plug in ax plus b, then the antiderivative will always have 1 over a in the antiderivative. Okay, so that's the first two. Let's look at the third one. The third one is when you have a constant over what we call a repeated linear factor. So we have a linear factor 2x plus 1. To say it's repeated means it's raised to some integer power like 2 or maybe 3 or maybe 4, something like that. How can we handle this? Just a u sub, yes, but we want to do it even quicker. So we have 1 over 2x plus 1 squared dx. This looks a lot like what? 1 over u squared, which is really like u to the negative 2. But, and I can only say that because this is linear, all right, inside. It's the only reason I can do it that way. If this inside was something else like quadratic or cubic, that method would not work. So I know I'm going to have to come through with the 1 over a. What's a for me here? 2, right? The 2 in front of the x. And then I need to take the antiderivative of what would be the equivalent of 1 over u squared, which is the same as the antiderivative of u to the negative 2, which by now we all are comfortable, hopefully. Negative u to the negative 1, or you could say plus c. Negative 1 over u plus c. Now the part that I wrote down here is not something that I would expect you to write down. I would expect this to actually be mentally done at this point, that you can do the antiderivative of u to the negative 2 up there. Okay? So I should just be able to go straight. Here's the 1 over a. Then I'm going to have what? Times negative 1 over 2x plus 1 plus a constant. See, no natural log because it was squared, right? Because it was squared, it does not work out to natural log. This one does because this is like 1 over u. This one's like 1 over u squared. Then you could put this together. We good or not? Shall we use our polling feature since we have it? Yeah, sure. Let's go ahead. Just tell me if you're on board or not. Okay. What's your quick question? That's too slow. Yes.
Where that a is coming from, what is that?
The u is the entire expression. The entire linear expression would be our u. But see, if you do that substitution, you're going to get a du of 2, aren't you? And you'll have to get rid of that 2, so you have to multiply by 1/2. But all of that now is kind of built in. We're trying to get that as just like a mental step now, instead of a formal substitution we have to make. So here's another example. Did I answer your question?
Yep.
Okay. X minus 5 to the third power dx. Again, this is a constant divided by what? A repeated linear factor, right? A repeated linear factor. And whenever I have something like that by itself, I look at that and go, that's kind of like 1 over u cubed, isn't it? 1 over u cubed. So I mentally come in here, and say, what would the antiderivative of 1 over u cubed be? Well, I know that 1 over u cubed is really u to the negative 3, and I know that the antiderivative of u to the negative 3 is negative 1/2 u to the negative 2 plus a constant. So this is just power rule, isn't it? Okay, so that's what I've done mentally. I've said, all right, that's the antiderivative. However, because I always have to compensate for that a, I need to make sure I address that. What was my a in this problem? 1. So because of that, I don't need it, right? Don't need to worry about it. So what would my antiderivative here be? Negative 1/2 x minus 5 to the negative 2 plus c. Could you write that with the x minus 5 down in the denominator, positive exponent, yes. Either way. The point of this is that we're trying to see what we can handle quickly, because when we see problems later today, they're going to be pretty complicated, and our goal is going to be to split it up and make each piece look like one of these. And then when we get to those, we're like, okay, we can do that. All right, so now, next one. The fifth one here, integral 1 over x squared plus 9 dx. Now, what did I write here? I put here that here we have a constant 1 divided by a quadratic, but our quadratic has no x term in it. It has no x term. You see that? It has x squared, but there's no x term. So, you recognize that? Doesn't that look like formula 17? Doesn't this look like 1 over u squared plus a squared du? Except it's 1 over x squared plus 9, which is 3 squared, isn't it? So a for us in this is what? In this problem is 3. So this just directly from formula 17 should be 1 over a arctangent of x over 3 plus a constant. Now, I didn't put this next one on your paper, but let me see if you could do this. That looks a lot like 1 over u squared plus a squared, doesn't it? The u you have in here, though, is linear, right? Well, we can do what we did in the previous problems. Is the only issue when you have a linear factor in there like that is you have to adjust for the a. That's the only thing you have to adjust for. So I can treat this just like the problem above, except instead of x, I have all of this in here, right? All of that in there. The only difference is that I need to come in with the 1 over, what? 2 to begin the whole thing, to compensate for this 2. I'm going to write it down, and then I'll ask you if you get it or not. The 1 over 2 comes from the fact that there's a linear thing in there. Then I need the formula. What's the formula for for formula 17? 1 over a, but a now is, be careful, it's 3, right? These are like two different a's. This a is the a from the linear part, and then this a is the part from the formula, which is our 3 squared. Arctan of 2x plus 1 over 3 plus c. Okay, just let's do a quick poll, see if you follow that. I may have stretched a little bit on that one. If that was 2x squared plus 1 in there, couldn't do it. Couldn't do it. Cool, couldn't do it that way. Okay. All right, let's take a look at number 6. I'll say one more thing about number 5, this first one. If that had been a minus between there, you could not have used this formula. Formula only works if there's a plus. All right? If there's a minus, well, we'll deal with that, okay? Just not yet. Okay, this is the form. What we have here is a constant over what? A quadratic. But there's something else about this quadratic that I want to point out. It's irreducible. What do I mean by irreducible? Can't be factored. not over real numbers. You could factor it over imaginary numbers, but that's not what this class is about. So you cannot factor this, all right? So how do we attack this? So I'm going to show you, all right? I'm going to show you this, and this was, if you did the last problem on your homework from last class, they told you to complete the square. Okay, that's exactly what I'm going to do here. Okay, I'm going to take, sorry, that little red dot's really bothering me. I should be bothered by all these dots everywhere, but that red is really bothering me. All right, so I'm going to complete the square. This is a technique that is often talked about in college algebra, and it is very, very convenient and useful, especially in calculus 2. All right, in college algebra, you kind of don't really see why you need it, but now you'll see hopefully why it's going to help. So here's what completing the square does. You take any quadratic that's written like this. So I mean, you have an x squared term, you have an x term, and you have a number. So you have a quadratic trinomial, 3 terms. Our goal here with completing the square is to be able to rewrite this so that it's something squared plus, or it could be maybe minus, some number which we'll call k. All right? That's the goal of completing the square. And inside here, inside this parentheses, guess what you're going to have? You're going to have something like x plus or minus some number b. So it's going to look like this right here. Problem we just did, right? If you complete the square, you should probably be able to then do the problem the way I did number 5, the second part. All right, so let's go through the technique of completing the square. So what we do for completing the square, make sure it's in descending order. Identify the coefficient in front of x. Figure out what that is. Write it down. Then do what to it? Divide it by 2. Always. Always, always. So divide it by 2. What would that give you if you get 1? Okay. Now, that's the first thing I'm going to do. The second thing I'm going to do, I'm going to take that 2, divide it by 2 again. This time I'm going to square it, and turns out I get the same number. It's just kind of an uninteresting problem. I have 2 different numbers. One of them was just the 2 divided by 2, which gave me 1. The other one was that same answer squared. Now, if you do completing the square correctly, here's what will happen. You take your original quadratic, and what we realize is sitting next to this x is actually plus 0. So x squared plus 2x plus nothing plus 17 is the exact same expression. Agreed? Then we're going to make use of this second number we got here, this 1. And I'm going to rewrite this 0 using this 1 as follows. X squared plus 2x. Now tell me if this is true or not. Is that still 0 here? 1 minus 1? Yes? 1 minus 1 still 0? You do it with the second number. Yes. And it will always be whatever that number is. This number is going to always be positive, isn't it? Because it came from squaring something. You're always going to put plus the number, minus the number. You never put minus then plus. Okay, so if this turned out to be 9, you'd put plus 9 minus. That's 5 plus 5 minus 5. Now, the reason why we do this is because now these first 3 terms are a perfect square trinomial guaranteed. That means it will always break down to be something like this. And in this particular case, it'll be x, right? And then what's the other number in here? Plus 1. Now, Guess where this plus 1 actually comes from? It's the first number that you got here, and it will always be that first number. That's why I like to write it down. So if you would have got a negative 5 here, this would have been minus 5. This, of course, would have been 25, but that doesn't matter. Okay, so that accounts for the first 3 terms, doesn't it? What about the next 2 terms right here? 16, right? 16 plus. No equals 0. Yep. But that brings up a very good point that I'll address here in a second. Let's see. Give me a poll if you follow that or not. What's that? The formulas? Which ones? The ones on there? You are allowed to use that packet on your test. Yes. That one's memorized, yes. It's used so much. We'll talk a little bit more about what you can have on the test. I plan on providing you with the 3 different trig sub formulas. That is, yes. Okay, all I did was completed the square, right? Let's go back to the integral, right? I'm going to just rewrite this integral right here with the denominator replaced with this. I'll do it on a new page. We have integral 1 over x plus 1 squared plus 16 dx. And now that looks again like that highlighted part there is like my u. It's like a 1 over u squared plus a squared. That's formula 17. Now I do have to account for this linear piece, right? What's the number in front of x? 1, so I don't need to come in with anything. So this will be, you tell me, 1/4 arctan x plus 1 over 4 plus c. There you go. Now let me address something. How many of you had seen completing the square before this? You don't have to vote, yes? Okay, how many of you remember completing the square where you take that number in the middle, you divide by 2, you square it, and then you were told to add both sides, add that to both sides of the equation? Yes? What's wrong with that? That's right. So what's the difference here? And why didn't I do that? Why didn't I take this 1 and add it to both sides of the equation? What equation? What equation? It's not an equation. And that's why in college algebra you should be taught this way, plus 0. You should not be taught add both sides, in my opinion. Because you don't have an equation all the time. This always works, always, because you can always do it to the expression. All right? So it's a danger to say add it to both sides if there's not an equation, especially if the quadratic is trapped underneath the square root, because then you really don't have an equation. You can't be adding things to both sides. So I hope that you follow this adding a 0 thing and that you adopt that as your way of doing it, because if not, I'm not quite sure what you're going to do. Introduce an equation all of a sudden, that won't make a lot of sense. So does that kind of get what I was saying? Because you said something about 0, right? Equals 0. Well, where's that coming from, right? Okay, hidden 0. Next one, 7. Integral x, whoa, what happened? X minus 1 over 4x squared minus 4x plus 3 dx. Okay, so the type, you tell me what the type of this one is. You have a linear expression on top of a quadratic expression. Is it irreducible? Can you factor that? It does factor? Okay, we're not going to factor it, but it does? Okay. Here's the approach that I'm going to start with, all right? Anytime you see a linear expression like that divided by a quadratic, here's what I recommend you do. You're going to make a substitution every single time of the denominator. Now, if the denominator is a quadratic, the derivative of it should be what? Linear, right? So what's the derivative of this? 8x minus 4. I'm going to put that in parentheses, dx. Do you agree? Okay. What's wrong with that, though? We don't have 8x minus 4 on top, do we? No, we do not. We do not. So although this substitution looks promising, it's not, the derivative's not there, right? Yet. So now I'm going to force it to be there. So this is a little bit of massaging that I'm about to do, all right? I really want, I'm going to start with the coefficient on x. I really want an 8 there, don't I? I really would love to have an 8 right here. So I can't just throw an 8 there, but what I can do is I can come out on the outside of this integral and I can multiply by 1, can't I? So why not 8 over 8? And then distribute that 8 through, and then wouldn't I have an 8x up there? But then I'd actually pick up a what? Minus 8 also. Okay, I'll deal with that in a second. So I'm going to come in here. I'm going to put 8 over 8, but I'm really only going to write 1/8 down here. I'm going to pass the 8 through the top. Like this. And remember, my goal is to get what up there? Minus 4. Right now I have minus 8. Now I've got the 8x, so I'm cool with that. I'm happy. Now, watch what I'm going to do. So what am I introducing to the problem? What we refer to as a hidden 0, all right? Just like you've always known that next to everything is times 1, right? You can always take something, multiply it times 1, it's the same thing. You've been doing that since forever, right? College algebra and before. Realizing a hidden 0 is a more advanced idea. Have I said this to you already yet? No? I'm saying it now. I'm stressing it. That is a major leap, all right, in terms of math, when mathematicians were trying to figure out stuff. Realizing that there's a plus 0 next to everything is used all the time. Okay. Especially my math majors. Any math majors? Hidden zeros, man. It's a big deal. It's how you prove a lot of different theorems. You say, oh, but that's plus this, and then that thing in there, you can make it whatever you want, as long as you do plus it and minus it. Okay, so what I'm going to do here is I really want to what? Minus 4. I'm going to put a minus 4 plus 4. All right? 1/8 still sitting out here. Minus 4 plus 4. What did I still have out there, though? Negative 8. And then all over 4x squared minus 4x plus 3 dx. Well, how about that? Well, yes, but we're not going to do complete square. All I'm doing now is I'm saying, hey, look, what we were going for was 8x minus 4, wasn't it? We got it. But we still have what over here? Negative 4 on top? All right, I'm okay with that. So 1/8, how about I write this way? 8x minus 4. And then what's the 4 minus 8 going to be? Minus 4? Minus, this is just minus 4, right? Okay. Tell me, I don't know how far I want. I'll just do this. I think maybe someone's probably sitting there going, hey, I really didn't need to do minus 4 plus 4. I kind of knew that negative 8 could be rewritten as negative 4 minus 4. But sometimes the numbers are not that obvious. And so this hidden 0, again, I'm trying to stress that's what you're doing. It's a hidden 0 in there. Well, no. I'm not completing the square here. Nope. All I'm doing is, I said I had a linear over quadratic. I said, I like that. My u is the quadratic. The derivative of that is linear, but that doesn't match what I have up top, right? Didn't match. So I tried to force the top to look like this. Multiplied by 8 over 8. Said, I just need a negative 4 here, so I subtracted and added 4. When I did that, I created that 8x minus 4, just like I wanted. The problem is, I still have a minus 4 here, and there's a 1/8 on the outside, but that doesn't matter. So let's go and address this now, because I'm not done. Check it out. Check this out. Like I said, the robotic little things are pretty impressive. Maybe not as much as this, though. I'm kidding, right? 4x squared, yeah. Try that. Okay. Now, all I did was split the integral, right? Right down that center line. I took these two terms over the denominator. I took this term over the denominator. I have two separate integrals. I brought the 1/8 to both integrals. Now, tell me about this first integral. It's u sub, and it's actually exactly 1 over u with du right there, isn't it? So this is just going to be natural log of u, right? All this stuff. And then the 1/8 in front. So you see how clean this first integral becomes? That's awesome. I'll have a plus c. I'll throw it on to the end. But what about that next integral? You could bring the negative 4 out. And then if I take the negative 4 out, I'll have negative 1/2 integral 1 over 4x squared minus 4x plus 3 dx. Yes? Look at number 6. How did we do that when we had a constant over the quadratic? What did we do? We completed the square. So guess what we get to do now? We get to complete the square on that one. But I want to recap, because, I mean, we're definitely not done, but I want to recap that this original problem was different from the previous problem in one aspect. It had an x up here instead of just a number. If it was just a number, we could complete the square like we did on the previous problem. But with that x in there, now we have that linear expression. You're actually going to have a better time with this if you do this first, massage it to make it look like you want, and split it into two new integrals. One integral is easy, relatively speaking. That's just a basic u substitution, 1 over u du. The second one is now something that we've already done. Yes? Okay. The 1/8 was in the beginning when this is what I had. I wanted an 8 in front of the x to match this. So I multiplied the top through by 8. But if I multiply by 8, I have to divide by 8. So this is really like an 8 over 8, but the 8 got passed through on the top. Because I can't just multiply by 8, it changes the problem. I can multiply by 1, which is 8 over 8, that's okay. Are you raising your hand? Substitution? What's your substitution going to be? Where's du, though? See, that's why this one's so great. Here's u. What's du? 8x minus 4. Hey, there it is. But this one doesn't have that. See that? Well, we have to do it the way I showed you before. All right, so you ready? I'm going to complete the square on this one. So I'm doing some completing the square on this. All right, here it is. I'll do it in blue. Complete square. I take my 4x squared minus 4x plus 3. And it's not an equation, right? This is not an equation, so I'm got to work with the expression as it appears. Now, there's something about completing the square that I did not point out in the last time I did it because we didn't have it. The first thing you always do when you complete the square is make sure that your coefficient on the x squared is 1. You cannot complete the square unless this number right here is a 1, which it's not, right? It's a 4. So I will factor a 4 out first. How do you factor a 4 out of 3? Just make it a 3/4. Just do a quick visual. If you distribute 4 back through, you should get back this expression. Now, looking just inside the parentheses, that is a quadratic trinomial with the coefficient on x squared being 1. So I go and complete the square. I identify the number in front of x, which in this case is -1. I take that -1 and I divide it by 2. That's my first number, -1/2. Then I take that -1, I divide it by 2, and I square it, which gives me 1/4. Those are the two numbers that I'm going to use now. Anyone want to help me out? What should I do next? X minus, but then what? Yeah, you might want to take your time through this. I'm going to do x squared minus, I'm just going to put x. Here's my hidden 0 right here. But I'm not going to actually write plus 0 this time. I'm going to put in which of these numbers am I going to use? The 1/4, right? So I'm going to put plus 1/4 minus 1/4. Then what's sitting next to that? Plus 3/4. What do the first 3 terms turn out to be? These guaranteed to be x. Then come over here to this number, minus 1/2. That quantity what? Squared. What's still out here though? Minus 1/4 plus 3/4, so that's just 2/4, that's 1/2. So plus 1/2. Yeah? But all of that was sitting in a parentheses with a 4, wasn't it? All right, take a quick poll here, and let's see if you're with me or not. If you have a question, now would be the time. So this is just the denominator, right? Just like this. I'm not going to multiply this 4 back through. Why? If that 4 is sitting out here in front of this stuff in parentheses, can't I just pull the 4 out on the bottom? I could, right? Just pull the 4 out. So that's what I'll do. So I'm going back to this now, all right? This piece right here. In fact, I need to go to a new page, so I'm just going to grab all this, take it with me. Let's go. Okay, so the stuff on the left is done, right? That's not an integral anymore. That's actually the antiderivative. So I've got all that, 1/8 natural log 4x squared minus 4x plus 3. Okay, minus 1 what? 1/8, because the 4 came out from the bottom. I have 1 over, what was it? X minus 1/2 squared plus 1/2 dx. And what can we do with that? Formula 17. And keeping in mind that this right here is linear in here, so that's like a 1 over u squared plus a squared. And the number in front of the x here is 1, so I don't need to come in with the 1 over a thing. So let's see if we can go straight to this. I'm real curious to see what you're going to do with this. Minus 1/8 times, now the formula for this. 1 over a. What's a in your problem? Careful. Look, this right here is a squared, isn't it? That means a is the square root of that, which is 1 over root 2. Isn't it? Isn't it? If 1/2 is, look, if this was a 9, everyone's like, yeah, it's 3, right? If I say 1/2, everyone freaks out. If it's 9, you take the square root of 9, you get 3. If it's 1/2, you take the square root of 1/2. What's the square root of 1/2? Square root of 1 is 1. Square root of 2 is square root of 2. So it's 1 over root 2. Now, you could rationalize that. You could write it as root 2 over 2 if you want. Either way. You could do that too. I would leave it as a root. That's the book for a constant is going to leave it as a root. Okay, but what am I supposed to put here? 1 over a, right? So that's the reciprocal of a, which is just root 2. So root 2 arctan of x minus 1/2 over 1 over, so a, right? So just, how can I write a down here? I can put 1 over root 2, couldn't I? I could also put root 2 over 2. So we have the negative 1/8 that came from the problem that was here to begin with. We have the 1 over a right here, which is root 2. I'm using this version of 1 over a, or of a. Then arctan of u over a, but I'm using this version of a here. Now the reason I'm using this version of a here is because I'm about to flip the 2 up and distribute it through there and leave the root 2 down here. When I distribute a 2 through here, what would I get? 2x minus 1. That's the way it would match the back of the book answer probably. This right here, if you were to just leave it like this, I'm okay. All right, on test, I don't care. Let me bring down the rest. I'm just going to box this and say we're done. Plus c. Root 1 over root 2, and then you divide that root 2 times x minus 1. If you don't rationalize it. If I don't rationalize it, root 2x minus root 2 over, yes. Yeah, and there's different variations of how you could write that, and they're all equal, so I don't really, not real particular on that. Okay. Let's vote, yay or nay on this. We've eaten up 50 minutes of the class, and we haven't done anything in partial fractions. Yes? Yeah, you could factor 1/8 out. All right, so let's just kind of take a step back for a second. Everything I've done today has required you know a Formula 17, and that you can complete a square, and that you can recognize patterns, right? In this problem, you had to massage it to look the right way. Yes? Now, I want to show you something because I've had students in the past ask me this. The original problem had x minus 1 on top, right? And then 4x squared minus 4x plus 3 dx. I'm going to do this real quick, all right? I've had students ask me, why not just do this to start? My answer is, you can. But here's the problem. This one over here is going to require what? Completing the square, which we had to do in the version I did, right? Yes? Okay, this one, we would have to get it to look like the derivative on the top, right? So I'd have to multiply the top and bottom by what? 8 first, and then that 8 would distribute through and you had 8, right? So that's gone. And then you would also need what here? Minus 4 plus 4, right? And then you would have to split it, wouldn't you? And then look, that 4 over this is another constant. And so you would have a completing the square that you would have to do here. So you actually would do completing the square possibly twice, unless you combine them together now. But if you do it the way I did it, you did it all in one step. So the answer would be, yes, you can, but you're going to have to do a little bit of tweaking of it. You might do double work if you're not careful. I hope that made sense. All right, what else is on our sheet here? Our holy sheet. Oh, this one. My goodness. Okay, this is good. I'm just looking at this problem, and just for a moment here, I'm having a complete, I have no idea how we're going to do this moment, which is good. Can you relate? Oh, I remember now. Yes. All right. Wait a minute, I lost it. So what do we have here? Tell me what we have. A linear over a repeated quadratic. This is a quadratic, right? But it's being repeated because it's being squared. So that's what I think I put here. Linear over repeated, not only is it repeated quadratic, it's irreducible. In other words, you cannot factor x squared plus 1. Okay, what would u sub get us here? If u was what? You want to try x squared plus 1? What's the derivative of that? 2x dx. Do you have 2x dx up there? Can you have 2x dx up there? Yes. If you split it up, how can you get a 2x up here? Multiply 2 on top and bottom. Distribute the 2 through to both. Let's see if this leads us there, okay? 2 over 2 integral x plus 1 over x squared plus 1 squared dx. Distribute the 2 through. 2x plus 2 over x squared plus 1 squared dx. So you have a 2x up here, but you also have what? Plus, oh, forgot the 1/2 outside, yes. You also have a 2. Well, can't I split this into 2 separate integrals again? And one of them I can do. Like one of them is going to be the basic U substitution that was recommended. So let's see how where this goes. I have 1/2 integral 2x over x squared plus 1 squared dx. The other integral is plus what? 1/2 again, and then 2. So why don't I just make it a 1? Okay. So just 1 over x squared plus 1 squared dx. Questions? What did we say? What can we do on this integral? U sub. This is u, right? Just that? What's the derivative of that? 2x dx. We have it on top. So that really looks like 1 over u squared. Antiderivative of 1 over u squared? Careful. U squared, not u, right? Negative 1 over u. That's it, right? Negative 1 over u. But then we have the 1/2 out front. So what I'm getting at is this integral is doable. This integral is 1/2 times negative 1 over x squared plus 1. I don't need that in parentheses. That's a basic U substitution. Let's see if you understood that, because I feel like I'm starting to lose some. The antiderivative of u to the negative 2, right? You have to account for that negative. Yeah, the antiderivative has been done. There's no more integral sign. I'm holding off on the plus c. Wow. Well, any ideas there? Yes? Okay. Yes. In fact, we will be doing partial fraction decomposition, which is what this section is about. We haven't done it yet. The reason why we haven't done it yet is because at the end of partial fraction decomposition, we will get this expression. And we want to be able to do this when we get to it. See, partial fraction decomposition is going to allow us to get here. Our problem is going to be more complicated. And so this will be like a final step, and we'll look at that and we'll be like, whew, at least we know how to do that. Yes, it'll take us 45 minutes, but we can do that. You know what I'm saying? All right, so we're kind of at a hung up spot unless someone sees it. Okay, at least you're thinking of different things, right? Basic substitution, throw it out the window, right? You don't have a u du here. Integration by parts was the next thing. You need to see something and then something else's derivative, and then you can use the transferring of the derivative. What would you choose to be your u and your dv, though, if you did that? You couldn't use just this. You have to grab the whole thing. You would have to grab 1 over x squared plus 1 squared, and then take the derivative of that, and it would be a mess. And then the antiderivative of dx would be x. That may work. I'm not going to rule it out, but not really wanting to run down that road. Okay, so you see that if it was just like x squared plus 1 without the squared, you would be like, we're done. Now, don't write this down. I agree that this is the same. That's what that means, right? But if you have two things multiplied together and you want to take the antiderivative, you just don't do the antiderivative of each one. That's what makes the Cal 2 difficult, right? You can't do this. So you can't say this is arctan x times arctan x is an antiderivative. Okay, we're running out of options here. What was last class about? Trig sub? Can we use trig sub here? You bet we can. Because you could rewrite this as the square root of x squared plus 1 to what power? Fourth power dx. Right? Because if you take a square root and you multiply it times itself 4 times, it's equivalent to squaring it. Do y'all agree with that or not? Now, what's the substitution, the trig substitution that I use when I see x squared plus 1? X is, so I'm about to do trig sub over here. X is going to be a tan theta. In this case, a is what? 1. So this is just going to be tan theta. What's dx? Secant squared theta d theta. What is the square root of x squared plus 1 turn into? Secant theta. That's all on your notes from last class, right? Rewrite this integral. I'm doing my trig sub right here. What does this integral become? 1 over secant to the 4th theta times secant squared theta d theta. That it? Which is 1 over secant squared theta d theta. But 1 over secant is cosine. So this is cosine squared theta d theta, right? That's what this means? So this is equal to, I'm out of room. Quick poll, are you still alive there? Still going? All right, next page. This is just that one piece I'm working on. We're now at cosine squared theta d theta. And how do you do cosine squared? The half angle identity, the one that I screwed up. The one that I'm going to be punished for at some point in time. So I have not done any integration. All I've done is use the power reducing formula. It's called on there the half angle, I think. And I pulled the 1/2 out. I don't like that. What was my mistake? What did I do instead of this formula? I put an x there instead. So, all right. So that's it. Now just take an antiderivative of this. 1/2. What's the antiderivative of 1? Theta, because thetas are variable. Antiderivative of cosine 2 theta. 1/2 sine 2 theta. And then I'll have plus my constant, which is 1/2 theta plus 1/4 sine 2 theta. I'm going to continue this problem all the way down because I think this addresses some of the issues that may have come up in homework. Yes? Yes. Yes, but I'm not ready to point that out. I'm going to point that out after I get past the theta. Yes. I want to address why we cannot use that we have to change it. All right. So in order to do this problem, I need to know what theta is. So what was our trig substitution that we made? X was equal to tan theta, right? I want to know what theta is. Theta by itself. Take this equation, take the arctangent on both sides of the equation. You get, oh wait a minute, hold on, let me go back. Was it x? Yes, it was x here, wasn't it? X was tangent theta. I want to make sure it wasn't like u or something like that. We hadn't switched variables. So this will be arctan x equals theta. So I did not need a reference triangle for that part. The next piece of information I need to know is what is sine of 2 theta. And this is where the reference triangle would come in. The problem is that I know the information that I have, x is equal to tan theta, has to do with theta, right? Not 2 theta. This over here has 2 theta. So the only way I can get this to work out is if I either figure out what 2 theta is, like on my triangle somehow, or I turn this 2 theta into just a single theta. And so that I've highlighted the pre-cal, the part right here, which should be something you remember from pre-cal. Sine 2 theta is equal to 2 sine theta cosine theta. It's one of your double angle identities for pre-cal. It's on your formula sheet. I'm just going to leave that theta there for now. So this becomes 2 sine theta cosine theta. What is the advantage of you having this formula now instead of sine 2 theta? What's the advantage of this one over this one? Yeah, I can figure out what sine theta is off my triangle. I can figure out what cosine theta is. I could not figure out what sine 2 theta was, though. So now I'm going to draw my reference triangle. Theta's here. I know that tangent theta is x. Tangent is opposite over adjacent. So this opposite side should be x. This adjacent side should be 1. The hypotenuse then becomes x squared plus 1. And now I can pick up all the other trig information off of that. So I'm ready. I think I'm going to have my final answer here. 1/2, what did we say theta was? Arctangent of x. Then plus 1/2, because the 2 and the 4 reduce. And now what's sine theta? So times sine theta, opposite over hypotenuse, x over square root x squared plus 1, times cosine theta, which is adjacent over that, so 1 over this. What happens to those roots down there? Just go away. So I have 1/2 arctangent x plus x over 2 times x squared plus 1. I could distribute the 2 through. So these two together became x squared plus 1, then times 2, distribute through. Now this is part of the answer, right? Remember there was another part? The other part was right here in red. So my final answer is this plus this. Do you need me to write it down? You want me to write it down? Okay, I'll write it down. It was negative 1 over 2 x squared plus 1. The one on the end? Would I want you to? No. Yeah, you could. If they have the same denominator, you could. Could we have done what? Okay, so yeah, let's go back and look at that. Let me make sure. I'm going to take a poll here and just make sure everyone's okay with this. Any questions? How? How what? 2 squared. These are multiplied. So it's like when you take something multiplied, it's like squaring it. So you're squaring a square root, the square root goes away. These two together become x squared plus 1. And then this 2 goes and distributes through. Yes? Theta doesn't have to be. Yes, you could do it on any. Does not matter. Nope. It's just usually most convenient to go back to the one that you had information on. Okay, the question that was being asked though was in the very beginning of the problem, which I don't remember where that was. was, could you have done your trig sub here? Yes, but let's see what would have happened. All right? This is a good question. I'm not convinced yet that it would be better. In fact, I think I see something that would cause a problem. So if we did our trig sub, it would be the same trig sub, wouldn't it? We'd say x is equal to tan theta. We would say that dx is equal to secant squared theta. D theta. And then the square root of x squared plus 1 was secant theta. Okay, then this would become, on top, is that right? Tan theta plus 1 over, this was secant to the 4th theta. And then out here was secant squared theta d theta. Right? And now you cancel to the secants, so you would have tangent theta plus 1 over secant squared theta d theta. You could split this into two different integrals, right? If it was tan squared theta plus 1, we could. Yes. But that wouldn't do anything with this up here, though. If this was tan squared theta plus 1, it still wouldn't, nothing would cancel, right? Right. And then on top, I think I heard someone say, is this is secant squared? This is not right. It's because it's not squared. So you could do this, though. Plus, the next one would be what? 1 over secant squared, so cosine squared theta, d theta. And right here, I'm happy with that. I can do that. In fact, we just did that. This one would be sine theta over cosine theta over 1 over cosine squared theta d theta. So what is this? Sine theta over cosine theta, so tangent theta d theta. Sine times cosine. Yes. Yeah, this is a basic U sub. Antiderivative of that is 1/2 sine squared theta. What? Well, this is a good example of I thought that you were the one who suggested we do this.
Well, I didn't know. I thought of it right now.
But it worked, right?
Yeah.
Okay. I mean, I was going off of the suggestion. Yeah. It worked. Now you have a new idea. The new idea was to do the trig sub first, and it appears that you would still get there. Now, we have to verify. You have to go back and get theta from this, right? I mean, you have to get what x is, but you know what sine theta is, right? So you could recover that. You also have this one over here, which we just did. So there is still, I mean, this looks like there would be no problem doing that. Which one's better? Maybe this one. Maybe this one seems easier. But you would have had to have recognized that right off the top. And that's where the challenge becomes, right? I mean, I was leading you into this. We had been doing things where we were like trying to match this and go du and, right? So we were kind of fixated. We were narrowed down in that tunnel vision. That's what we were seeing. Now that we've done the problem, you step back, you see it could have gone a little easier, maybe another way. So it goes back to the analogy of, I always use this analogy in all my classes, trying to get from point A to B. I mean, we're trying to get from the front to the end, right? The beginning of the problem to the end of the problem. And there's more than one route that takes you there, right? And some of them go like this. Hold on, down here, right? And then eventually get back up there, right? And as long as you're following the rules of algebra, the rules of calculus, what you can and can't do using the identities properly, then you're on a path. Sometimes it seems like you're going in circles, but as soon as you break a rule, then you're no longer on the path, and the only way to get back on the path is just by luck or by re-breaking a rule and going back on accident or something. But so I think the path that we just took was possibly this one the first time, and now we see that there might have been another way. But you know, that's what's challenging about grading things like this too, is that there are different approaches, and they can all be the same, they can all be correct, and your answers might even look different. So it's difficult to grade something like this. So, and that we ran into that with the homework, right? I had some students come to me asking about trying to look at the solution in the back of the book versus what they're doing, and they don't look the same. Well, because you use slightly different techniques and things look different. So very good. I'm glad you pointed that out. It's a good lesson. I still think that I would have wanted to have seen it done this first way, just so you could see it. All right. Well, wow. Have I done the 8 problems? Yes. Okay, now, if we see any of these 8 forms, we're actually going to get excited because we know how to do them now, right? What's that? Do you think you could do 8 problems in an hour and 40 minutes? Yeah. Yeah. So hard to test in this class. It's so difficult. Take-home test, yeah, right.
No, so I had for Cal 1, that was the question that we asked. What do you do for Cal 3 too? Like, they usually have a take-home.
Cal 3 is all take-home usually. Yeah. Okay, let's try in the last 20 minutes just to at least get some of the language down here, talk about rational functions and this whole thing called partial fraction decomposition. So you'll recall from college algebra that a rational function is a ratio of 2 polynomials. That is a function p of x divided by q of x, where q of x is not 0. Here are some examples of rational functions. So we have cubic function over a linear function, quadratic over a cubic, quartic over a cubic, quadratic over a cubic, quadratic over a quadratic. These are just all examples of rational functions. And our goal is going to be to integrate them. Find the antiderivatives of these. All right? That's our goal. Now, do any of these fall into the form of the 8 that I just gave you? No. 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 And no. So none of these fall into the format that we have, that I've shown. A strategy for integrating rational functions. This is a strategy, which means it is a recommended approach. Try and follow this. Things will go a little nicer. The first thing you do for a rational function is make sure it's not easy, like the 8 we just did, or like the first 2 or 3 where they're like natural log or something like that. Make sure it's not one of those first. Then inspect the degree of the numerator and the denominator. What's the degree? What is the degree of something? Highest power, right? Highest power. So you're going to look at the numerator, look at the highest power, look at the denominator, look at the highest power. If the degree of the numerator is less than the degree of the denominator, you're going to move on to the next step. If the degree of the numerator is greater than or equal to the denominator, you must first do long division. That will give you a new expression that'll be easier to work with. All right? Then, after you've done that, for the remaining rational functions, so after you do your long division, or if you didn't have to do your long division, you're going to have a rational function sitting there still somewhere. For that one, we are going to use partial fraction decomposition, which is something that is taught usually in pre-cal. How many of you saw partial fraction decomposition in pre-cal? Yeah? Let's do a vote. I'm curious to know. Let me ask you this first. How many of you took pre-cal here? Yes or no? Pre-cal here. Okay. Now, of those 22 people, of the 22, how many of you remember partial fraction? Not remember how to do it, but remember that you did have to do partial fraction decomposition. It's right at the beginning of the semester. Yeah, AX plus B, all that stuff, yes. Okay, so for the majority of people who are here saw it. Okay, now, the people who did not take pre-cal here, there should be what, like 4 of you? Did you see partial fraction decomposition in pre-cal? Yes, no. Oh, wait, hold on. How many people do we have in here now? All right, let me ask this again. The people who did not take pre-cal here, there should be like 4 of you, I think, 5, whatever. Did you see partial fraction decomposition? Yes or no? Okay, fine, whatever. So, a majority of the class has seen partial fraction decomposition at some point. I will remind you briefly how it's done in words, and it sucks when you look at it in words. It's better to see it in practice because it makes a little more sense. I think it's a little cleaner just to get into examples, all right? But we have to have a way of explaining it, so here it is. With partial fraction decomposition, we're looking for certain things. We have certain cases of what we can see. So if your denominator has n, that's not right. Should say has n. Has n distinct linear factors. That means who cares what the top is, all right? You've already done long division if you needed to. Who cares what the top is? Your denominator is a bunch of linear things, and each one of them is different, distinct. Then what you will do is you will rewrite this thing as, here it is, as a letter. Usually we use like A over that first linear factor, B over the second linear factor, C over the third linear factor, D over the fourth linear factor. Now, in this notation, I'm using subscripts. Why do mathematicians use subscripts instead of just saying A, B, C, D? How many linear factors could I possibly have? 1,000. You can't use A, B, C because you're going to run out of letters, right? So we use the subscripts because you'll never run out of subscripts. That's why all these formulas look so nasty, because we have to account for more letters than we actually have in an alphabet. Okay, so that's what we do. Should we try one of those and we'll just end class on just that? We'll get into the rest. Let me see if I have one that's good. Yeah. Let's try and do the first two. I'm going to give you integral x cubed plus x over x minus 1 dx. Starting to think ahead. This is an exam. You're sitting here, you're looking at that, you're thinking, is this a basic formula? Is this a basic substitution? Is this integration by parts? Is this a trig integral? Is this trig substitution? Is this partial fractions? Well, I have a rational function, right? So I first check the degree of the numerator, which is 3. Degree of denominator is 1. It's higher on top than the bottom. Long division goes first. Long division goes as follows. If you need to go back and review long division, you can. I suggest you do if you need to. You rewrite the numerator. putting zeros to account for any spaces where you don't have powers of x. So I rewrote x cubed plus x as x cubed plus 0x squared plus x plus 0. And I'm dividing that by x minus 1. Then we ask ourselves, how do I turn x into x cubed? What do I need to multiply by? X squared. So I'm going to line that up over the x squared here. And then you distribute your x squared through to each of these. X squared times x gives me x cubed. X squared times negative 1 gives me negative x squared. Then you come through and subtract this line. So when I subtract, that becomes a negative 3x, or x cubed, sorry. And that negative x squared becomes a plus. I'm like overly exaggerating the signs because I changed them, right? And now add straight down. When you add down, what do you get? Just x squared. Now you play the exact same game. How do you turn x into x squared? Multiply by what? X. So I line that up here, x, and then distribute that x through to each one of these. So you would have x times x gives you x squared. Put it underneath. X times negative 1 gives you negative x. Put that down here. Come through and subtract, which means you change the signs again. Now, I've seen different people do this different ways. Do you see how when I added, oh, where's my little cursor? See when I added down here, I brought the x squared here. I did not bring the x down. Some people do bring that x down. When I add this, I look all the way up, and I just go x plus x is, or actually, yeah, x plus x is going to give me 2x. So we might have different variations of how we do long division. I'm just pointing that out. That's the way I do it. I bring it straight all the way down, add down, I get 2x. And that's it, right? Well, I mean, that's it for that. Okay, now, play the same game. What do I have to multiply x by to turn it into 2x? Just plus 2. Multiply through 2 times x, 2x, 2 times negative 1, negative 2. Come through, subtract, and what would you get? 2. Play the same game. What do I have to multiply x by to get 2? That's when you stop. You stop when the power here on x is bigger than the power out here. So this is my remainder, 2. So I'm out of room up here. Here's the way I should write that. It should be x squared plus x plus 2 plus what? The remainder over the divisor. 2 over the divisor, x minus 1. And this, yes, this is the division, right? So I can replace this right here with this expression. That's my new integral. Am I happy about that? You bet I am. Because look, this is just what? Power rule, power rule, power rule. This one? Simple, constant over linear. So my antiderivative is 1/3 x cubed plus 1/2 x squared plus 2x plus 2 natural log x minus 1 plus c. I think that example shows the advantage of using the long division. It takes a very complicated looking thing that would be very difficult to integrate and turns it into a bunch of easy things to integrate. We'll do a quick poll on that one, see if you were okay with that or not. We've got 10 minutes. I think I have enough time to start the next one. I know you all want to go. Look, I want you to get your money's worth here. You know?
Right, like I'm good.
All right. Let's try this one. This one will not need long division. That's the good news. Well, I can do this problem. We can do a quick quiz. What do y'all want to do? Just do this problem? All right. Quiz? Just do a quiz. All right, so we go through all our different things. We go, okay, look, this is looking like a rational function. Let's see, do I need to do long division first? No, because the power on top is smaller than the power on the bottom. So I can't. So now I'm going to start to look and see if it follows into one of these cases. The first case, and the only case I've talked about, is where we have distinct linear factors in the denominator, which means you must be able to factor the denominator. So let's see if you can factor the denominator. I'm going to do it on the side here. I see a common factor of x that I can pull out of everything. And I'm going to hope that this factors. Does it? What is it? 2x, x, plus 2, was it minus 1 there? That is the factorization of the cubic polynomial in the denominator. And that means that this can be turned into this. Now, here's where the partial fractions comes in. All we've done right now is factored the denominator. That is it. Partial fractions says that we are going to, I'll list out here on the side. We have 3 distinct linear factors, don't we? In Q of x. That's our denominator. In our denominator, we've got 3 distinct linear factors. Whenever we have that situation, we rewrite the problem. Now, notice I'm not bringing the integral in here. I'm just looking at the integrand. I'm going to work with that, get back to the integral when I'm done. So now I'm back in pre-cal, and I'm being asked to break this up. So what I do is over here, since I have 3 distinct linear factors, for each linear factor, I will create a new fraction. On the bottom of these fractions are the 3 distinct linear factors, x, 2x, minus 1, and then x plus 2. And then on top are numbers that I don't know yet. So we'll call them A, B, and C. And it's okay. If you want to use A1, A2, A3, you can. I'm using A, B, and C because I'm never going to give you a problem that has more than 26 factors in it. You'll probably never have more than, like, 15. So, no, I'm kidding. Well, you could have a repeated linear factor, which would count as more than 1. So, and that's, okay, so that's the setup of the partial fraction decomposition. Anybody remember what you do now? Multiply both sides of this equation by the LCD. The LCD is this. So what happens if I multiply this side by this? All you get is the x squared plus 2x minus 1. Now you take this whole thing and you multiply times this first fraction on the top only, right? So that's going, that yellow thing's going right in here, and right in here. And when I put that yellow thing in here, the x cancels out of that, right? And all you're left with is the a, and what other factors are still there? 2x minus 1 times x plus 2. What would be our next piece out here? B's there, X is there. X plus 2 is here. The last one, C x 2x minus 1. Now, look, why in the hell am I doing this? If I knew what these numbers were, right? If I knew what these numbers were, then I'd be able to rewrite this entire integral as a number over linear, number over linear, number over linear. 3 separate integrals. They're all trivial integrals. Do you see that? That's the whole point, is to try and rewrite it so that it's hard to see that in pre-cal while you're doing that, right? In pre-cal, you're trying to, it's like, why in the world are we doing partial fraction decomposition? Because in Cal 2, when you do integration and you want to go integrate a nasty rational function, you're going to do this to make it easier, break it into easier integrals. I hope that all makes sense. Okay, now, how do you go and get A, B, and C from here? There's 2 different approaches. There's the short, easy way that doesn't always work, and there's the long way that always works. Yes? That's the short, easy way that doesn't always work. So let's try that one first. Let's go short, easy. Okay, the short, easy way doesn't always work. So I'm putting a little asterisk next to this. Okay, does not always work. Is that you try and just get your A, your B, and your C separately. So if I want to try and figure out what A is, I want B to be gone, I want C to be gone. That means I want this whole thing to go away, I want this whole thing to go away. How can I make this whole thing go away and this whole thing go away if I'm allowing you to let X be whatever you want it to be? If X is 0, right? If X is 0, this is going to kill this whole term, kill this whole term. Will it kill this term? No. And on the left side, we just plug 0 in. So what we're going to do is have a little bit of what I like to call the God complex. It's one of the few times in math where you get to come in there and just say, let it be. Like, just let X be 0. Let it be 0. By my choice. You have control for just this moment. All right? Let X be 0. There we go. What's the left side of this equation become? -1. Then you have A times, plug your 0 in right here. -1, plug your 0 in right here. 2, and then we already said it would kill those 2 off, right? I'll just put plus 0 so you're aware. And this just means -2A equals -1. A is positive half. That's it. Now you go find B. Same way, if you can. Can you get B? This is what I did to get A, right? Let's get B now. To get B, I want to kill off the A and the C. Yeah, I can only use the 2x minus 1 factor to kill those off. So X is 1/2. So you're trying to look at what does B, well, how should I say, what does the A and the C one have that the B doesn't, is what I'm looking for, the 2x minus 1. Set it to 0, you get half. Let's take a vote while I'm writing this down. X is 1/2. I just want to see if you're still there. I know you're still there, but what am I doing? I've got 1 minute. I'm going to do this. All right, when we plug this in, you have to plug it in all the way across. So 1/2 squared, 1/4, plus 1 minus 1 equals, the A1's dead, the C1's dead. Plug 1/2 in here, you get B times 1/2. Plug 1/2 in here. 1/2 plus 2 is 5/2. 5/2. So you have what? 1/4 equals 5/4 B. Yeah. B is 1/5. I'm going to squeeze the C one right in here. Trying to get it all on one page. What will I do to get C? I will let X be what? Let X be -2. Plug in here, we get 4. Then take away 4. And then so just -1 equals the first 2 terms are gone. Plug in -2 here. What do you get? C times -2 and then -5. So the right side's 10. Left side's -1. So divide through. You get C is -1/10. I'm sorry. I'm going to hold you an extra minute. I mean, I can't. Well, oh, yeah, that's right. My watch is a little fast. Then I'm going to hold you an extra 3 minutes because I want to hold you longer. No. All right, so our original integral here. This integral turns into the A over this, B over this, C over this. Here we go. The original integral now turns into the A. What was A? 1/2. I'm just going to write it like that, over X, plus the B. B was 1/5 over, what was the factor for the B one? 2x minus 1? Plus the C, which was -1/10 over X plus 2 dx. And notice the way I wrote the A, B, and C. I didn't care that they were fractions. Because what I'm going to do is, when I go to integrate this, I'm going to pull the 1/2 out. Just set it in front. And then just do the antiderivative of 1 over X. So what's the antiderivative of 1 over X? Natural log X. So I have 1/2. Here's natural log X. Next one. Be extremely careful here. The 1/5 comes out. What's the antiderivative of 1 over 2x minus 1? 1/2 natural log 2x minus 1. But then you had the 1/5 out there. It's 1/10 natural log 2x minus 1. And then minus 1/10 natural log x plus 2 plus C. We have made it. Whew. I don't have a homework assignment for that yet. I will go to my office. I'll email you what problems you could start looking at in that section. What's our deal with our schedule? Are we when's our test? March? No. I'm looking at our thing. Today we were supposed to have finished 6.2. We are ahead. That means next week all I plan on doing is coming in here and just giving you problems and just giving you, like, not giving you any indication of what type of problem they are, and just you work on problems in class. There'll be grades, but I mean grades for effort and participation. The first test covers everything, including the hyperbolic and the inverse trig, but I would say 90 to 95% of the test is techniques of integration.
So 6.3 is not going to be on it?
Oh, no, everything's on it. Yep. Yep. 6.3. We'll finish 6.3. Yeah, I'll do more, but next week will just be all, after I finish 6.3, it'll be more practice.
Go back up to your original A plus B plus
Yes, I will. Yep.